Okay, so we got ourselves an optimization problem, this one here, but there is a constraint. There is a constraint, and the constraint is this constraint. And this basically means that all the points are correctly classified. Okay? This is exactly what this says. Remember, this is the same as that. After we introduce the yi. So we have constraints. That's one thing. But and we know that optimization with constraints calls for famous Lagrange multipliers, which you should know from the calculus refresher course. But there's one little thing here that I have not explained in the calculus refresher. That is that the constraint here is an inequality. And the constraint here is an inequality. Yeah. So this means all points correctly classified. Okay. So this means that we have something we call KKT. This is the Karush-Kuhn-Tucker condition. Yeah. So basically we do the same as we do in Lagrange with equalities. Yeah. So we define a Lagrangian that is a function of WB and the multipliers alpha, and that is equal to, our minimization is half W squared. Yeah. And then what I'm going to do here is I'm going to bring the 1 to the other side. So first we do minus and then the sum over these alpha i's. These are the Lagrange multipliers. And then times yi W transpose x plus b minus 1. Okay? So we minimize. Yeah, we minimize. We minimize over w and b. Yeah? And there is a condition here that comes from KKT, means that the sum of the that the alpha i's are greater or equal than 0. I'm not going to prove that, but it's part of the KKT condition. All right, this is our objective function, or Lagrangian, and we want to minimize over w and b. And these are your Lagrange coefficients, and there's many. There's a sum over I. So I goes from 1 to m. These are the training samples. And because we deal with a constraint that's an inequality, we have an extra condition, is that alpha i's need to be positive. This is what we call a KKT condition, Karush-Kuhn-Tucker. Yeah. Okay, I've not discussed Lagrange multipliers with inequality constraint in the calculus refresher, but this is how it works. So what we're going to do now is we're going to minimize this function with respect to w and b. And once we found expressions for w and or b, we'll put them back in here, and then we will maximize over alpha. This is how you deal with such a problem. So let us take a look at the derivative of L with respect to W. And W here, the 2 comes to the front, so this will be just your vector. And then minus the sum over alpha I. And the only term with W is this one, so alpha I, yi, xi. Yeah? Yi, xi. This we're gonna set to 0. So that means that W is nothing more than alpha I, yi, xi. And it's a linear combination of the samples. Yeah? So it's a linear combination of the samples. This is our first expression for W. Now let's see what we find out if the derivative with respect to B, no B, so this is 0, so I have minus the sum. The only term with B is here, so B, yi, alpha I. So alpha I, yi is the derivative. And this we also gonna set to 0. So that means that the sum over alpha I, yi equals 0. This is another expression that we have. Okay, so now we're gonna put these two in there, and then we're gonna maximize over alpha. So our Lagrangian now becomes only a function of alpha. It's W and B free. So equals half W squared means that this is the sum over I, alpha I, yi, xi, and then another sum over j, alpha j, yj, xj. This is the first term. Then we have minus the sum over, so I need to replace a w with, so alpha I, then we have yi, and then we have this w, but now we're going to put j's, alpha j, yj, xj, and then times xi, yeah, times xi plus b, and this is like this, minus 1. This is this bracket, okay? Minus 1. So this is equal to, we have here still half of the sum over I, alpha I, yi, xi, and the sum over j over alpha j, yj, xj. This remains the same, and then minus, I have here the sum alpha I, yi, xi, yeah, alpha I, yi, xi, times the sum over j, alpha j, yj, xj, okay, then I have the term alpha I, yi times b, but alpha I, yi is 0, so I have 0, and then the last term, this minus and this minus become a plus, so we just have the sum over alpha I. Okay? So, let us now rewrite this. So now we're going to maximize over alpha I, alpha j, this expression, which is a Lagrangian only depending on alpha. And this is half. So you see these two are the same here. So half minus 1 is minus half. Let me put this one, sorry, and this must be a plus. Let me put this one first, alpha I, and then minus half, yeah, because half minus 1 is minus half, And then I have these expressions. So I have the sum over I, the sum over j of alpha I, alpha j, yi, oh sorry, yi, yj, and then xi, xj. And we know that alpha I needs to be positive, and the sum over alpha I, yi is 0. Now, this is what we just derived